Hello everyone, this is wrang. In this class, let's talk something about parallel computing. In today's lecture, I will cover some knowledge, some basic knowledge about the principles of parallel algorithm design. You know, parallel computing is not a very new concept, but it didn't get its popularity until until recent years, thanks to the rapid development of hardware and software design. Nowadays in some big data center or some big communication data center, they rely so much on the parallel computing. So let's begin today's lecture about a parallel algorithm design. In this lecture, I will cover six parts. The first will be some preliminaries about parallel programming. The second part is about decomposition techniques and characteristics of tasks, and interactions will be the third part. And the first part is mapping techniques, and the fifth one is minimizing interaction overheads, and the last part will be parallel algorithm methods. Okay, let's begin with some items or preliminaries in parallel computing. Okay, so here I want to talk about decomposition as our first item. In many computing tasks, it usually to be very huge that will take a lot of time to finish it. So that's why we want to divide it into some small subtasks. In this way, we can finish every small parts one by one and then combine the results together so that we can get the final results of the huge task. Okay, here uh, the first step in developing a parallel algorithm is to decompose the program into tasks that can be executed concurrently. Uh, a given program may be decomposed into tasks in many different ways, and about the dividing techniques, we will talk about this information later. And the tasks may be the same, the different, or even intermediate size. And a decomposition can be illustrated in the form of a decorated graph with nodes corresponding to tasks and edges, indicating that the result of one task is required for processing the next. Such a graph is called task dependency graph. Okay, the second item is called granularity of task decompositions. This term is about the number of tasks that can be divided into. So decomposition into a large number of tasks results in fine-grained decomposition, and that into a small number of tasks results in a coarse-grained decomposition. We can think about this term as how small, how big one task can be divided into small tasks. The degree of concurrency is the number of tasks that can be executed in parallel is the degree of concurrency of decomposition. Here we have some specific terms called maximum degree of concurrency and the average degree of concurrency. We can get hand of these two items literally because you can get its meaning by its names. The critical path length is a directed path in the task dependency graph represents a sequence of tasks that must be processed one after the other. We can see it's a workflow. Okay, the longest such path, this means the shortest time in which the program can be executed in parallel. And at the same time, the length of the longest path in a task dependency graph is called the critical path length. This definition is very important for us to determine the subtask sequence and its granularity. The task interaction graphs is about how the information or results is conveyed or transported during different subtasks. Um, and processing and mapping. This part is about how to assign a data set into a node or into a worker. Here we want to design this mapping techniques with different disciplines. One is that we want to minimum idling and optimal load balance, and as well we want to get the minimum communication between different nodes. In this case, we can save a lot of time and we can save a lot of bandwidth. Appropriate mapping must minimize the parallel execution time by mapping in different tasks to different processes, assigning tasks on crucial paths to processes as soon as they become available. That means we don't want to have a huge idling time and minimizing interaction between processes by mapping tasks with dense interactions to the same process. And here, let's talk about part two, decomposition techniques. So here we have mainly have four techniques about decomposition. One is recursive decomposition, data decomposition, exploratory decomposition, speculative decomposition. Let's talk about those one by one. First, let's talk about recursive decomposition. Um, usually this method is suitable to solve the divide and conquer strategy. We mentioned the divide and conquer. I think you have got enough information and knowledge about this kind of algorithm design in some other classes. So I will skip this part. I think it's very similar to the theory behind the divide and conquer. Okay, data decomposition. Here we can divide the huge task uh, by their data size or data site. So we can identify the data on which commutations are performed and partition this data across various tasks. This partitioning includes the decomposition of the program. Data can be partitioned in many ways, and the techniques we choose will critically influence the performance of the parallel algorithm. So data decomposition, we can use one strategy called output data decomposition. Just as its name shows, we can divide the task about the output data, a partition of the output across tasks, decompose the program initially, and here we have another strategy called input data partitioning. This method can be used if each output can be naturally computed as a function of the input. This is the this is the very important uh, 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 it's a very important factor for us to use this kind of decomposition methods. And in many cases, this is the only nature decomposition because the output is not clearly known in advance. And a task is associated with each input data partition. The task performs as much of the computation with its part of the data. Subsequent processing combines these partial results. And here we have the third method called the intermediate data partitioning. Computation can often be viewed as the sequence of transformation from the input to the output data. So, given this situation, we can often divide the task by their intermediate data site. And here we have the second speculative decomposition. You know, in some applications, dependency between tasks are known in advance. So in this case, it's impossible to identify the independent tasks. There are two approaches to deal with such applications. One is called conservative approaches. Another is called optimistic approaches. This kind of approaches may have a little different in the concurrency and in the performance. So here let's talk about hybrid decompositions. Often a mix of decomposition techniques is necessary for decomposing a program. But here let's take the two examples. One is called quick sort. A recursive decomposition alone limits concurrency, so a mix of data and recursive decomposition is more desirable. And then our second example is the discrete event simulation. There might be concurrency in task processing. A mix of speculative decomposition and data decomposition may work well. Even for some simple problems like finding a minimum of a list of numbers, a mix of data, and the recursive decomposition, this kind of decomposition, hybrid decomposition can work well. And let's talk about the third part is about characteristics of tasks and interactions. So the task here we can see is the computing computing mission a computer or node should complete. So the task characteristics include task generation, task size, and the size of data associated with this task. Task generation can be divided into two different categories. One is called static task generation and dynamic task generation. So the first generation, the first type generation is when about concurrent tasks can be defined in advance, and dynamic task generation we don't know its specific workflow or processing sequence in advance, so it's dynamic. And the task size is, task size may be uniform or non-uniform. Non-uniform task size may be such that they can be determined in advance or not. Uh, Examples about the uh, task size is the discrete optimization programs, in which it's difficult to estimate the effective size of a state space. And the size of data associated with tasks is the size of data associated with a task that may be small or maybe large when viewed in the context of the size of the task. A small context of task imply that an algorithm can easily communicate this task to the other process dynamically, but for the large context, it's not very easy to make communication or convey it intermediate data. And here we can talk about the communications of task interactions in four different categories. That's the static interactions, dynamic interactions, regular interactions, and irregular interactions. Okay, static interactions mainly about the task and their interaction are known in advance. So it's annoying. We can say it's a little easier for the program to design its algorithm. And the dynamic interactions is the timing or the interaction task cannot be determined in advance. So it requires a lot of time to think about how to format your program and how to pass in messages between different nodes. Regular interactions is a definition pattern to the interactions. This pattern can be exploited for efficiency implementation. And irregular interactions mean interactions lack well-defined topologies. Here we can have some more specific uh, features about the task interactions. In this slide, it mentioned about if this interaction is read only or write only or both. I think it's very easy. You can read this slide later by yourself. And the mapping techniques. In this part is mainly talk about how to assign a task into a specific nodes or specific computer. Once the program has been decomposed into concurrent tasks or maybe subtasks, these tasks must be mapped to processes that can be executed on parallel platform. Mappings must minimize overheads and the primary overheads are communication and idling. Minimizing these overheads often represents contradicting objectives. Assigning all work to be one processor is usually minimize communication at the expense of significant idling. So, in the design of any algorithm, uh, we mainly want to have a good time, but uh, we have to put into more computers or more memories. And so we have to find a trade-off between the time and the memory. Wrapping techniques for minimum idling. These techniques can be static or dynamic. Static mapping is about tasks are mapped to process in advance. Dynamic is we don't know or the workflow or the processing sequence in advance, so we just map the task to the process it at runtime. Other factors that determine the choice of techniques include the size of data associated with the task and the nature of underlying domain. So the schemes for static mapping is can be based on data partitioning, can based on task graph partitioning, or here we can have a third method called hybrid mappings. Okay, mappings between mappings based on task partitioning is partitioning a given task dependency graph across process and determine an optional mapping or general task dependency graph is NP complete program and excellent heuristics exist for structure graphs. So This method is mainly based on the dependency graph. So if we want to design a better program, we have to study the dependency graph deeply and find out should which one should finish first and who will be the next one, and how to convey their results from step one to step two. Hierarchical mappings is sometimes a single mapping because sometimes the single mapping techniques is not enough. So that's why we want to combine different mapping techniques together. So to get a better performance or to be time consuming. And schemes for dynamic mapping. Dynamic mapping is sometimes also referred to as dynamic load balance, since the load balance is a primary motivation for dynamic mapping. Dynamic mapping schemes can be centralized or distributed. Uh, I think more information can be found in later chapters. Centralized dynamic mapping as processors are designed as master or slaves. I think this for some cloud computing platforms such as Hadoop and Spark, they mainly applied this kind of mapping method. They have a master node and some different slave nodes. The master node will take control of all the cluster. He is responsible to assign and reclaim all the resources and get the final results. The distributed dynamic mapping is each process can be sent or receive work from the other processor. So in this kind of model, we don't have a master or we don't have slave nodes. Every node is the same. They are in the same hierarchy level. So the fifth part is minimizing interaction overheads. Here we just want to minimize the data locality, minimizing the volume of data exchange, and minimize the frequency of interactions, and minimize contention and hot spots. That's the four main tasks for minimizing interaction overheads. And here we can overlapping communications with interactions. Use non-blocking communications, multi-threading, and prefetching to hide latencies. Here we can republishing data or computations and use group communications instead of point-to-point primitives. Overlap interaction with other interactions. Here is some method we can use to minimizing interaction overheads. And the last part, we will talk something about parallel algorithm models. Here, we may have two kind of models. One is called the data parallel model, and the other is task graph model. Data parallel model is that tasks are statically or semi-statically mapped to process, and each task performs similar operations on different data. However, task graph model is starting from a task dependency graph, and the interrelationships among the tasks are utilized to promote locality or reduce the interaction costs. So here the two kind of parallel algorithm models is very widely used. We can't see which one is better or not. So it's the specific problems determine which method should be used. So it's meant about the some basic conception of parallel algorithm design. Um, Hold on. Anchor.